logarithmic derivative, and when y, and again, so we have been studying logarithmic derivative and also derivative of a sine function, inverse sine function. So let's do something more. So if y is arctangent x, and probably you have learned how to take a derivative of arctangent in your freshman years, right? So anybody remembers how to calculate the inverse tangent? Raise your hand. Arctangent. Or at least to remember seeing the derivative. I mean, it's supposed to be covered in freshman calculus, 미적분, right? And you don't remember? Right. 1 over 1 plus x squared. So actually, since y is the inverse tangent or the arctangent, we say arctangent. The arctangent is inverse of tangent. So x is tangent to y, right? Which is sine y, cosine y. So easiest to calculate the derivative is you calculate dx dy first. So that is dy d sine y times cosine y plus sine y dyd over cosine y. And since we have learned how to calculate the composite function's derivative, so this is cosine y times 1 over cosine y plus sine y. This is minus cosine square y minus sine y. So this is composite function. It's like dx d g hx gx, right? Chain rule that we covered last week. So it is 1 plus tangent to square y, right? And tangent y is x squared, right? Because tangent y is x. We want to calculate dy dx, which is actually 1 over dy dx 1 plus x squared. So that's how we calculate the derivative of arctangent x. Also, if y is arc cosine x, we can do the same thing. X equal cosine y. So dy dx is minus sine y. Square root of 1 minus cosine square y. Square root of x. So dx dy is actually dy dx square root 1 minus x squared. So this is probably the easiest form of differential equation. Another So I'm reviewing some of the stuff for the inverse sine function, the inverse trigonometric functions derivative we covered last week. And toward the end of the class, we also covered the following form of a derivative: fx dx dfx, which is logarithmic derivative. Actually, this is very important. So we are going to see the importance of the logarithmic derivative soon, but before that, the topic is differential equation. So this is about the differentiation part of the calculus. You need to know for the following up the differential equation part that I'm going to cover in this semester. So how many of you feel comfortable up to now for the derivatives? I mean, you are still not comfortable to calculate derivative? Maybe it's, you might need to have a quiz next week then. Okay, it's a joke, maybe 2 weeks. We will have plenty of time to differential equation. What is differential equation? Differential equation is an equation or set of equations which involves derivative of unknown function yx, that is dx dy dx squared d squared y dx n squared dn y. So differential equation is a set of equations that involves or that contains derivative of unknown function y. So dy dx dx squared d squared y dx n squared dn y. So I'm going to call this y prime as dx dy, y double prime y to the n dx n dn y. So we are going to find the following order of a derivative. For example, when you have dxn, dny, nth order derivative. And degree, power of a derivative. For example, dx dy square is called the first order, second degree derivative. And we say if the highest degree is greater than 1, we call the equation is nonlinear. So if degree is greater than 1, we call this differential equation is nonlinear. It doesn't matter whether the highest order is degree of the highest order or degree of the lowest order derivative is greater than 1. Either way, we call this differential equation nonlinear. And nonlinear differential equation is extremely difficult, and we are not going to cover that. So you can be relaxed. This is part 2. Part 3, we will focus on linear differential equation. The linear means highest degree is 1. Okay? And this DE is a differential equation, acronym for I don't have a unfortunately. So maybe there's a way that I can use. So differential equation means D dot E means differential equation. It's called acronym. Acronym. Acronym is a shortened word. 약자. Synonym. Antonym. So acronym is a shortened word. Synonym is a similar word. 동의어. Antonym is a opposite word. 반의어, right? So you're learning some English in addition to math. Right. So for example, this is the simplest type of differential equation. And fortunately, in this case, you know the answer, right? Y is arctangent x. But also, some constant can be a solution as well, right? Because the dx tangent x plus c is 1 plus x squared. So you can have additional constant as a solution. Or in high school, you might have learned this way. The opposite of differentiation is integration. So another approach is actually just y is some differential equation. That's another approach that we learned in high school. There's the opposite of a derivative. But basically, it's a first order derivative. So for example, dx dy is minus square root 1 minus x squared. Then you know the answer, right? Y is cosine inverse x plus c. Some special case. Or, let me see. It may be easier to write this way. Instead of writing this, if a differential equation is given by the following form. That is dx d ln x, right? ln actually fx. Then y simply ln fx plus some constant, right? And there are common things about this differential equation. What is the highest order of the derivative for this case? The first one? 1, 1, right? And what is the highest order of degree? 1. So those are the typical example of linear first order differential equation. This is called 1, 2 linear first order ordinary differential equation. So ordinary means there is only a derivative regarding to x. Ordinary means with respect to x only, or one variable. Of course, you learn partial derivatives in your freshman year, right? The function is of f, x, y, z. Then you can take a derivative for the x or y or z, right? So maybe we can do some more review. Am I going too fast? Or, okay, is my handwriting too fast? So I'm not going fast, but my handwriting is fast. Okay. Yeah, actually, some of my colleagues told me that I write very fast. So I try to write as slowly as possible, but I cannot guarantee. Some more review. Ordinary derivative. Ordinary derivative. Y equal of the form. So a function is given y is a function of x only, and we have take the derivative with respect to x only. So dependent variable y is a function of single independent variable x only. So ordinary derivative is case for the dependent variable y is a function of independent variable x only. So in that case, we call this ordinary derivative. On the other hand, so how many of you have heard about partial derivative? 현미분. So only 2? How many? 2, 3, 4. So most of you never learned about partial derivative in your freshman years. So you didn't take freshman calculus? Perhaps next time I should take freshman calculus to teach you, to let you know better. So partial derivative. So it's a case of this applies to the case of a dependent variable is a function of x, y, z, etc., etc. So for example, u when we can define partial z partial u is delta goes to 0. Same, f u x y z plus delta minus u x y z. And likewise, partial x partial u defined as delta goes to 0, delta u x plus delta y z minus u x y z, and partial y partial u is same, delta goes to 0, delta u x y plus delta z minus u x y z. So take an example. When u is given by x, y, z, then partial x partial u is by definition delta goes to 0, delta u x plus delta y z minus u x y z, right? So this delta goes to 0, delta x plus delta y z minus x y z. So this is delta goes to 0, delta delta y z y z. Now you're familiar? So anybody remembers how to take the partial derivative? Now raise your hand. Okay, a little bit better. Partial y. Same, right? So delta goes to 0, delta x y plus delta z minus x y z, which is actually delta goes to 0, delta x delta z is x z, right? Delta xyz plus delta minus xyz xy. So summary, if u xyz is xyz, then partial x partial u was yz, right? Partial y partial u is xz. Partial z partial u is xy. So now so when you take the partial derivative with respect to x, then you just treat y and z as a constant. So, for example, partial x, treat yz as constant. Likewise, partial y partial, treat xz as constant. Partial z partial y, treat xy as constant. So let's make another example. I'm still writing too fast. For example, another example. X squared plus y squared plus z squared. So what is partial x partial? So when you take, I don't have a pointer. And let me see if there is a function that can be used as a pointer here. There might be. Is this? No. What is this? Okay. All right. Can you see? X. So we are taking x, partial derivative with respect to x. That means we are taking this y and z as a constant, right? So that's simply 2x. Partial y partial u, simply 2y, partial z partial u, 2z. What if we have a complicated case? U, x, y, z turns out to be function of g, x, y, z. So partial x u is actually u gx plus delta yz minus u gxyz, right? So we can say 3x plus delta gz as g plus delta x. So then this can be something like this, delta g. Delta g. So delta goes to 0, delta g plus delta g minus u g delta g delta g. You can do that, right? You can always do nothing. Multiply by 1 or multiply by something and divide by the same thing. When delta goes to 0, delta g also goes to 0, right? So it becomes delta goes to 0, delta g goes to 0, delta g, u g plus delta g minus u g, delta over delta g. So this is basically g x plus delta, g delta minus g x y z. So it becomes dg du partial x partial g. So likewise, partial y partial u is dg du partial y partial g. Partial z partial u is dg du partial z partial g. This is called chain rule. Anybody remembers that? Raise your hand. You probably had learned during your freshman calculus. How many of you remember that? Few students remember that. Nice. So this is called chain rule. Called chain rule. We are basically just reviewing the part that we covered, you learned in your freshman years. So for example, ux I don't know. So u is something like square root of x square plus y square plus z square. Oh. So you can call this whole thing as a g. Then what is dg d root to g? Right? Remember that? And partial x partial g is what? 2x, right? So partial x partial u is dg du dx dg is square root of g is x square plus y square plus z square 2x x z. Then likewise y 30. Y z z. Even though we have taken a surprise quiz last week, today is also seems like we have penetrated this row. Maybe we can lock the door and take 5 minutes, 2 minutes actually, surprise quiz. So please lock the door. Then this two. So this is going to be a surprise quiz, and write your name and serials at the top. The problem number 1, write my name. Okay, my English name is this. So question number 1 is write your name. It's going to be 5 points. That's it. My name. Or okay, it could become your professor's name. Okay? You have to write your name on the top and write my name, which I wrote down. It's 5 points. The surprise quiz score actually goes to the denominator, not in denominator. So it's actually quite good, right? You can improve your percentage. So total score covers the quiz and final. And whatever the other things comes to the denominator. So are you ready to? So let's collect it. Collect the paper. 5 points. 난 노터빌라 뜬다고 했으니까. CRC 핸드북이 올려놨나? CRC Actually, I forgot to turn off the record, so perhaps I will continue. How about now we have a square root in the denominator. So how do we calculate the derivative? So let's start with this. Square root of x. You can also use a chain rule, for example, hx as a square root of x. Then y is hx, right? So dx dy th d h times dx dh. So if we differentiate 1 over h by h, we get minus 1 over h squared, right? And dx dh is dx d root 2x is minus hx squared is root x squared. And this is twice of root 1 over 1, right? So minus twice of x square root x square root of x. So likewise, when you set g, x squared plus y squared plus z squared, then partial x partial u is dg du partial x partial my handwriting is, I don't know, it's partial dg du partial x partial g is minus 2 g square root of g is x squared plus y squared plus z squared square root of x squared plus y squared plus z squared times 2x. So that is minus x squared plus y squared plus z squared 3 over 2. So this actually arrives from the potential. Likewise, partial y, partial u is minus x squared plus y squared plus z squared 3 over 2y partial z partial u minus c right. I think most of you might have taken general physics in freshman, right? 일반 물리? 안 배운 사람 손 들어보세요. If you haven't taken general physics, raise your hand. So most of you have taken the general physics. So if there is a charge at the origin, there's a point x, y, z point. This is charge. potential is 4 pi epsilon 0 x square plus y square plus z square square root over q. So that is a potential, electrostatic potential. 전기 potential is called you might have learned this during your freshman physics in the second semester, in the first month probably. So you might have learned this about 6 months ago. An electric field those are the electric field. 전기장. Component. And now you can calculate those partial derivatives, right? Because we have done that already. So it turns out that electric field is minus, this is a constant, 4 pi epsilon 0, x square plus y square plus z square, 3 over 2 x, and etc. etc. So the reason why we are learning differentiation is so partial derivative, differentiation allows to define Hofstad's electric field. So before I proceed, I may just briefly take a detour. 1650, discovery of calculus by Isaac Newton. So 1650, the Isaac Newton discovered calculus. It was about the same time the German mathematician called Leibniz also discovered this, but it's not, so mostly historians, Newton is known. 1765, let me check my number. James Watt. Do you know who is James Watt? Let me check the date. James Watt. Okay, 65 is correct. Steam engine. Remember? So James Watt was able to invent steam engine because he could solve differential equation via solving differential equations. So that's very important. So steam engine is an impetus of industrial revolution, right? So actually differential equation is behind. And differential equation can be solved because calculus is known by Newton. So Newton is actually the figure. He also formulates the mechanics, right? 역학. Newton was, so those are the mechanics and calculus are the behind of the foundation for this industrial revolution. And that's the reason why we are learning differential equation, because those are very important events. In 1850, James Clerk Maxwell formulated electromagnetic theory. So after another 100 years, James Clerk Maxwell was able to formulate electromagnetic theory. He was 16 years old at the time. 16 years old. He's a genius. So he formulated electromagnetic theory, and 30 years later, 1880, Michael Faraday, remember anything? Invented how to produce electricity. Electricity. And one of the prediction is electromagnetic wave. In 1894, I think, Hertz microwave communication he invented. So those are the very important events happened in the last 100 years. I think the most important event was the calculus. So calculus, 1865. Calculus was invented by Newton. He also discovered the mechanics, and then those two combined by James Watt, by solving the differential equations, and then he invented the steam engine. And with the advent of a steam engine, the modern industrial revolution, we can build automobiles, factories, and mass production things. So everything started with steam engine, and if we trace back it all goes back to the calculus and mechanics. And then those theoretical tools allows James Clerk Maxwell in about mid-19th century to formulate the electromagnetic theory. And the two things he predicted. One is one can produce electricity, and another one is one can produce electromagnetic wave, which is propagating through the space. And about 30 years later, Michael Faraday actually followed Maxwell's theory and then invented electricity, and then now we can use all this electricity, right? So if any of those events happen, what will happen? We might be still using candles for the lighting, no projection, no handphone, right? So currently IT revolution is always, so those things actually contribute to modern IT. So that's the first phase of history. 1, 2. The first phase of its technical development was triggered by the discovery of calculus and mechanics, and with the steam engine, and then its impetus for the Industrial Revolution starting in the late 19th century. And then about 100 years later, after the invention of a steam engine, James Clerk Maxwell formulated electromagnetic theory. And from that, two things came out. One is electricity, 전기. The other one is wave, microwave. So we can communicate through the space or long distance communication. And there is an old saying that history repeats itself. So next phase might be 1925 quantum mechanics. Was discovered by many Bohr, Dirac, Heisenberg. So that will also be the foundation for the next generation of a revolution with, I would say, quantum computation. Will be maybe next revolution, maybe. Next revolution. So this may be phase 3 in the history. So over the period of 400 years, starting there's a little history, and we can actually go trace back. There has been rumor that actually Pythagoras also invented calculus. But for some reason, the discovery of calculus is suppressed. For many reasons. Actually, religious world there's a lot of dominant factor, so it's called dark age. So it could actually, industrial revolution could happen actually 1500 years earlier, 1500 years earlier than James Watt. If those inventions, discoveries by Pythagoras and others in calculus was not surprising. There was a big fire in the Alexandria around this time. Big fire at Alexandria Library. Destroyed most of the mathematics and scientific discoveries. So those are the very sad part. So there is many rumors that Pythagoras actually discovered Newton's calculus in BC 200, about 1800 years before Isaac Newton did. And there was also a rumor that Newton actually accidentally discovered the old material, old mathematics books from the Greek period, and then he rediscovered the calculus after almost 2,000 years later. So, and Dark Age was around 1,000 years, and under the name of religion. So that's. So I'm not very anti-religion, because from the historical background, that the religion suppressed most of the scientific discoveries during the last 2,000 years. So you can imagine that if those things did not happen, maybe we could have, if the Industrial Revolution happened maybe 1,500 years before now, then many things could happen. So that's a bit of a sad story. But maybe it's time to go back to our main study. So where were we? We are spending. So you must be familiar with partial derivatives now, right? So let's study linear. First order ordinary differential equations. Okay, so from now on, I'm going to just write down this as ODE, as an acronym. RX. For example, tangent very, very complicated, right? So the idea is say maybe something simple. Sorry. QX. Lambda x, y, lambda qx. By so idea is oops. What is this? No. No. Without why is this not working? So equation 1 is a general form of a differential equation. I make it the coefficient of the highest order is 1. Then still the example is very difficult to solve, right? So idea is we multiply by equation 1 as some function lambda x and then make it form like 1. So we call this integrating factor. Called integrating factor. And see what happens. So we have a px y equal qx and multiply by lambda x, we have lambda x dx dy plus lambda x pxy lambda x qx, right? 1, 2. By the way, dx d lambda x y is dx d lambda y plus lambda dx d y is lambda qx. So we like to set equation 2 and 3 are the same by setting 2 is equal to 3. We have lambda x dx dy, lambda x px y, lambda x qx is same as lambda dx dy plus dx d lambda y, right? So these two actually cancel each other, and this has to be the same. So lambda x px is dx d lambda, right? Or 1 over lambda d lambda dx d lambda is p is dx d ln lambda. So we can solve the differential equation by setting the logarithmic derivative of ln lambda equal to p. That you learned logarithmic derivative a long time ago, right? So logarithmic derivative is all you need to find the solution for the first order differential equation. Okay? So idea is to find, so I'm going to repeat it again, so maybe I'm going too fast. So are you following me so far? A little bit? I think it will be more clear when you take a quiz, because we have to study then. But I'm going to do it again. So, okay, given the equation y dx, maybe I should. Given step number 1 is find an integrating factor lambda x such that dx d lambda xy is same as lambda dx dy plus lambda pxy, right? And actually the solution is this: dx d ln lambda x is px. Then solve the following. Lambda x gx. lambda x y is lambda x prime qx prime dx prime plus c y is lambda x over c plus lambda x prime q prime x prime dx prime. That's the solution. Too abstract, isn't it? So that's the reason why we have been studying the logarithm derivative in the last week. That I was going to use this for this solving the first part of the differential equation. And so let's go back to the example. But I'll let you write down. So I'm not going too fast, right? Because I took some detour about the history of mathematics and the industrial revolution and modern technology, things like that. So example, dx dy cosine x over y is tangent x. Maybe we can start with the easiest one, 0. Also, the terminology differential equation is said homogeneous when the right half side is 0. So this is called if right half side is called RHS is 0. Or sometimes null. That's probably the easiest case. So step number 1 is find the lambda, right? So dx d lambda y is lambda dx dy lambda cosine x y 0. No, this is lambda. Sorry. This is so what is the secant x? Remember that? Secant x dx d ln tangent x plus the secant x, right? We covered this last week. Remember that? So this is your lambda, actually. So lambda y is constant. Y is actually c over tangent x plus secant x. That's the solution. So the first order differential equation is actually can be converted into to find the logarithmic derivative. Same is equal to find the logarithmic derivative. And another example is this. We can extend dx dy plus cosine xy, bit more complicated, tangent x. And if the right-hand side is non-zero, we call the ODE as inhomogeneous ODE. Inhomogeneous ODE. So when homogeneousness is zero, inhomogeneousness is non-zero. So let's try to do the same thing. Step lambda x. We know the lambda x, right? Already. Lambda x was tangent x plus secant x. So dx d lambda xy is actually lambda x tangent x. Tangent x plus secant x tangent x. Tangent square x plus secant x tangent x. I think my handwriting is horrible, so it's x. Right? So we need to utilize some of the knowledge of derivative. This is 2. What is dx d tangent x? 1 plus 1 plus tangent square x, right? What is dx d secant x? Tangent x secant x, right? So let's compare with this and this. I guess we can do nothing, right? Add 0. So we can transform this into tangent square x plus 1 plus secant x tangent x minus 1, right? This is 3. Then this becomes dx d tangent x plus dx d secant x minus 1, right? So lambda x y is actually tangent x plus secant x minus x plus c. or maybe we have small space 4. We can go this. So yx is actually 1 plus tangent x, secant x, c minus x. C is a constant. How about that? So, not very difficult to follow, isn't it? However, maybe we can take a break for maybe a few minutes. So first to the ordinary differential equation is basically the problem of finding an integrating factor lambda. So solving the first order ODE is equivalent to finding an integrating factor lambda x such that dx d lambda xy x is lambda x qx. So given differential equation is this, when given differential equation is dx dy px y equal qx. One, this is 2, and dx d lambda x yx is lambda x dx dy lambda x px y. So finding the solution of a first order ODE is actually finding an integrating factor lambda x such that 1 and 3 are satisfied. So 1 and 3 are satisfied by lambda. Simple. Consider the following derivative. And I think you should be able to do this easily. dxd is 1, right? plus this part is twice of x squared plus 1, twice of x, right? Is square root of x squared plus 1 plus x plus so this is also a very interesting property. X plus square root x squared plus 1 dx d x plus square root x squared plus 1. And this is nothing but the logarithmic derivative, right? So this is dx d ln x plus root x squared plus 1 1 over square root x squared plus 1, right? So this is a very interesting logarithmic derivative. So using this knowledge, we can try to solve this. Oh, maybe I can use blue. Zero y so we can transform this by using this way. So lambda dx dy plus lambda y is actually same as dx d lambda y. So ln lambda dx d is square root x squared plus 1, right? So lambda is nothing but x plus square x plus 1. So our solution is the following. Dx d x plus square root of x squared plus 1, y is 0, or y is some constant divided by this, right? So first order differential equation can be solved very easily by integrating factors. And one example is dx dy plus root x squared plus 1 over y is maybe x plus x squared plus 1 over x squared. How about that? We already know the integrating factor, right? Lambda x is x plus square root x squared plus 1. So our equation is the following. dx1 x plus square x plus 1 y is lambda x plus square root x squared plus 1 times x plus square root plus 1 x squared. So they cancel each other. X squared. So x plus square root x square plus 1 y 1/3 x square plus some constant, right? That so y is this x square plus 1 c plus 1/3 x square. So how do you determine c? Will be later. So the first order differential equation is basically logarithmic derivatives. So in order to find 오늘 올려놓을게요. 아마 밤에 올릴 것 같아요. 네. 아, 노는 날이에요? 우리 다음 주 수요일 날, 잠깐만. Next Wednesday is anniversary for university, right? So there won't be there won't be any class. No class next Wednesday. 수요일 날에 대우님이셨어? 네. 나는 몰랐는데. 네. 수요일 날 개교기념일이라고 수업이 없대서. 원래 수업이 없나?
네, 원래 수업.
그러면 휴강이 아닌 거지? 그냥 노는 날인 거지?